This lecture, we are going to talk about the seventh, I believe, number seventh handout of Laplacian matrix, and it is something called the bottleneck matrix. So we have heard of the adjacency matrix, the Laplacian matrix, and maybe you heard of something like a distance matrix, something like that. But anyway, this is a new kind of matrix that is associated with a graph, and particularly it is associated with a structure called rooted tree. But before giving the formal definition, I want to give you an example which is more concrete and help us to get into this area. So let's say we have a tree, and V is a point, a vertex of this tree. And L is its Laplacian matrix. Now, let's think of how does it look like. Say we have a tree. This is a tree T. And we say V is equal to 1. Okay, and then we can consider its Laplacian matrix. In this particular case, the Laplacian matrix looks like this. It has the one vertex that connects to its, which is adjacent to every vertex. Okay, now recall that we can consider this matrix L prime, which is L taking out number 1. Okay, taking out a particular vertex V. L taking out V, so which is this one. L prime is equal to L taking out V, which is just 3, 1, 1, minus 1, minus 1. Okay? And according to the matrix tree theory, we know the determinant of this matrix. The determinant of L prime is equal to the number of spanning tree, and which is equal to 1, right? Because the number of spanning tree inside the tree is just itself, which is just one tree. So the determinant of this particular submatrix is going to be equal to 1. So if you recall how to calculate the inverse of a matrix by its adjoint, there is a formula like this. You can do something called adjugate, and then divide it by its determinant. I'm not sure if I used this notation before, but this is the adjugate of L prime. And the idea of adjugate is you take out one column and one row and calculate its determinant, and then you determine one entry. So the entries of the adjugate is always an integer, provided that L prime is all integer, right? So the adjugate of L prime has all entries integer. And meanwhile, because determinant is equal to 1, so we know that the whole matrix, this is 1, and this is integer matrix. So the whole matrix, the inverse is again an integer matrix. Okay, so let's see if that's the case to double check if our understanding is correct, at least in this particular example. Now, we got this up to this stage, right? We already take out one vertex, which is one row and one column. Then let's calculate the determinant. if you calculate the determinant of L prime, you will see that it is basically equal to 1, I believe. 3, 0, 0, and minus 1, minus 1. So in the end, the determinant is equal to 1. And I cheat a little bit because I calculated beforehand. But if you believe me, the inverse of this matrix looks like this. And as I claimed before, this matrix, all of the entries are integer. And this is not so usual, you know. When you're doing the inverse of a matrix, basically, if you have 2, then you have inverse. If you have 2, then the inverse of 2 in terms of real line, it is 1/2, which is not an integer. But this is a special case that it is going to be an integer. So there should be some meaning about this. Okay, so we see that there are two features about this. The first one is that this L prime inverse is all integer. Okay. The second one, it is better than integer. It is actually all positive. So the question that we care about usually is there a combinatorial meaning of these numbers? Okay, for example, how to get this 2, right? Are you counting something else? Do you get this 2 by something else instead of just doing the inverse of the matrix? So that's all the topic that I want to talk about in this lesson, and we'll see what is the answer of this one. Okay, so we will go through these ideas one by one. Number one, it is all integer. We have seen this before already. If you want to calculate the inverse of this one, you have to calculate the determinant, and then you calculate the adjugate, right? And the adjugate, like what I say, you take out one column and one row, then this entry, the determinant of this submatrix is going to be the entry of the adjugate at this point. So the adjugate and the determinant is enough to tell you that it is all integer. And secondly, I want to tell you that it is always positive. And there is a theory behind that, so I want to state a more general setting to say that actually a lot of cases will be all positive. So this is a linear algebra fact. You can just think about that, even think about the Laplacian matrix. Okay. So if M is a matrix and it is an irreducible matrix, irreducible and a positive, semi-positive definite. And there is one more condition, with all off-diagonal entries to be positive. Less than or equal to 0. So let me emphasize, there are a few conditions. It has to be irreducible, but we are talking about the tree, so the graph is connected and it is irreducible. It has to be positive definite. This is not so easy to see that at the beginning, but if you look at this one, if you really calculate this one, it is positive definite. Okay. But anyway, let's focus on the linear algebra first. So suppose M is okay, symmetric matrix, and it's irreducible, and it is positive definite, and all off diagonal entries are 0 or negative. Off diagonal means not on the diagonal, 不在对角线上的。Okay, what can we say about that? Then the inverse of M is entrywisely positive. Okay, so notice that here is positive. Every entry is positive. Okay, and so this is an interesting thing that has quite a different way of proving that. So let's try to look at its proof. And in fact, it is part of your homework, but I'm just providing you the overall idea. The first thing is maybe you can replace M by some constant times M if necessary. Okay, you will see that all these properties are preserved after the scaling. If M is irreducible, then this is also irreducible. Positive definite, this is also positive definite, provided that N is a large number. Okay, and all entries negative, then this is all entries negative. So after you taking out the inverse, you know how to take out the inverse of this one either. So we can just scale any, do any scaling of the matrix M. It is fine. And by scaling, we may assume this M matrix has certain property. Such that the diagonal entries is not going to be too big. Okay, so this is one condition. We pick a large N such that the diagonal entries is very small. This should be doable. And also we want every eigenvalues to be small. Okay, so every diagonal entry is small, and also every eigenvalue is small. We just try to pick a super large N to make this happen. Okay, so now we have this condition, then we can do something more. The key idea of this proof is the following: is to consider this matrix, I minus M. Okay, now you think about this I minus M. The diagonal entries is less than 1, so all the diagonal entries are positive. So let's see what properties we have. This matrix is still irreducible, and it has diagonal entries is positive, and also its off diagonal entries is greater than or equal to 0. So this is a nice matrix, and every entry is either 0 or positive, and the diagonal entries are positive. Now we are going to use this formula. You can think of these things first. Remember, if R is less than or equal to 1, then the series looks like this: 1 over 1 minus R is equal to 1 plus R squared plus da da da, right? So we have the same formula for a matrix. We can consider I minus m, and then taking the inverse. You just think of this as 1, think of this as r, and think of the inverse as 1 over r, right? 1 over something. So this follows the same formula, and it looks like 1 plus r squared plus da da da, and keep going. And this sequence will converge to the inverse of the left hand side. But the inverse of the left hand side is exactly equal to inverse of m. Right? So this tells us that the inverse of m is equal to this 1 over 1 minus something, and it is equal to 1 plus something squared plus something cubic, and keep going. But the good thing is, in this case, you see every matrix is positive or equal to 0. Positive or equal to 0, positive or equal to 0. And meanwhile, it is irreducible. So for every entry, there is at least one of the power to make it non-zero. So in the end, this one is going to be greater than 0. And that's the proof. I skipped some of the details, but I think the main idea I want to convey is this formula, right? If you can recall this formula and you can make everything positive, then in the end you can make it positive. Okay, I skipped some of the details. Is there something not so clear at this point? Or we can discuss a bit later. Okay, so yeah, if you have question, we can discuss later, and let me finish the definition, the main idea in this lecture. Okay, now we take care of all integer, and now we also about to take care of positive. Why? Because this matrix, all the off-diagonal entries are 0 or negative, right? And also it is irreducible because it is coming from a tree. If you look at this matrix, it is basically equal to the Laplacian matrix of the subtree. You see the subpart of this part, like 2, 3, 4. But it is a bit different if you just calculate the Laplacian matrix, which is different from this one. What is the difference? It is this entry, just this entry. So the difference is that you have to add one more. Because this entry, there is a degree coming from the left-hand side, which is not counted, right? The degree is equal to 2 here, but this vertex has degree 3 in the original graph. And except for this, everything is the same. So this matrix is irreducible. The whole matrix is also irreducible. And this matrix is positive semi-definite, and you are able to prove that by Rayleigh quotient. The sum of them is actually positive definite. So this matrix has all the good properties that we have, so the inverse of it is all positive. Now we have it is all integer and it is all positive, then we are going to talk about what are the meanings of these numbers. Okay, so let me use the example. This is 1, and we call that as the root of this tree, and this is 3 and 4, and somehow we have this matrix L prime inverse is equal to 1, 1, 1, 1, 2, 1, 1, 1, 2. And recall that this is corresponding to R, corresponding to 3, corresponding to 4. Okay, and now let's look at what are these numbers. The ij entry of this inverse has a particular meaning, and it is equal to the number of common vertices between two paths. The path from I to R and the path from J to R. What does that mean? Here is a more concrete example. If we do, for example, I is equal to R, J, let me choose a different one. Okay, I is equal to 3 and J is equal to 4. Okay, so you will see this is R and this is I, this is J, and what is the path? The path from I to J, I to R is this one. And the path from J to R is this one. So we only have one common vertex. So you see that from 3 and 4, this entry is equal to 1. Okay? And how about why this is 2? We have I equal to 3 and J equal to 3. And let's look at the same graph again. Okay, so now this time I and J are both here, and so we have I to R is this path, and J and R is the same path. So there are two common vertex. So that's why we got the 2 at 3, 3 entry. So this is called the bottleneck matrix, and the reason it is called the bottleneck matrix is because all the vertices, if you look at this one, all the vertices want to go back to R. From I to R, J to R, and you are looking at the bottleneck part, which part is the common vertices. Every path will come back and merge together. When you merge together, that's the bottleneck part. Everyone want to pass through this part. And for this case, everything is on the bottleneck, which means that they share all the path, and they have two common vertices. And that's the meaning, the reason we call that as the bottleneck matrix. You are basically counting the number of common vertices between all the paths. So now let me give you the formal definition, and then we're almost done. For bottleneck matrix, we consider a structure called a rooted tree. And a rooted tree is just a pair, which is the T and the root V. Okay, and this V is we call that as the root. And the second definition is saying the Dirichlet operator. And whenever we call that the operator in algebraic graph theory, we just means a matrix. The Dirichlet operator of a rooted tree, we write that as L circle. and it is equal to the Laplacian matrix of T plus the matrix with the 1 at the VV entry. And we also know that this is actually equal to L of, I'm just drawing that, okay? Hope you can understand. We have a metric, we have a graph T, and then this T has a vertex V, okay? And we add one more leaf on here, it is still a tree. So we call this extra vertex as W. It is a new vertex. Now we can consider this matrix, and this matrix is a little bit bigger, and then we can take out the W afterward. Take out W, and then take in the inverse. So you can kind of forget about this definition, but pretty much it is the same idea here. If we want to take the bottleneck matrix of these three vertices, then we can do two things. The first thing is that use the 3x3 to add one more entry. The other way is to consider a bigger graph and then take out and then a bigger Laplacian matrix and take out one row and one column. So both of them are the same. 对，没有复音，谢谢。And the definition of the bottleneck matrix is just equal to the inverse of the Dirichlet operator. And the theorem says that the ij entry of the bottleneck matrix has the meaning we mentioned before. Say we have a TV, which is a rooted tree, and then B is the bottleneck matrix. Then the ij entries of B is equal to number of common vertices. Between two paths. Okay, so I think I will pause here